the question, okay, I totally misunderstood your question. So your question is, how do you use AI to help your work? Oh, okay. Yeah, that's totally orthogonal from for what we from what we are talking about here. And yes, there are an infinite amount of ways, but all these large language models, basically, the ones that are like the GPT-4 and this or one and whatever, they are already quite good at RTL, at all these things. You can definitely, so I personally use them extensively, and say, this, I mean, I'll give you an example. With one of my students, we were looking at, using a custom floating point number representation and doing basically an ALU, an other multiplier, a functional unit for that floating point number system. And to do that manually, the way, like now I understand your question, like in the old days, it would take a long time, yeah, with, if you go just to, regular ChatGPT and you tell, I want this custom floating point, with 4 bits of mantissa, 3 bits of exponent, that does, a sticky bit and all that. It will do all that. It will make some mistakes, but you will get, a very solid thing. Now, what you can, and by the way, all the companies, and that's kind of bad news for for some types of jobs. All the companies, that design chips, they are going one step further, and they do what's called fine tuning. And and there is this RAG. There are all kinds of ways to basically make this, because GPT is very general purpose, right? If you ask it to write a poem in Sanskrit, in the style of Tagore, they would do it. So, but you can specify, you can, and in my group, we are trying to get our own kind of, large language model that's fine-tuned for specific tasks. But yes, I mean, this is happening whether you want it or not. It's just, yeah, learning and accept. Well, one is accepting, there are still many people that do not accept in some sense that this is actually a positive thing and it makes you stronger and, more capable and more productive. But once you accept, then you need, it's like everything else. You need to learn how to use it. You need to be careful. There are pitfalls that you can fall into. But yeah, I mean, and this is the other kind of big problem, it's a very fast moving field. So, whatever we do or say today, is going to be very different in 3 months. But yeah, embrace it, and it's not going to be important at all very soon to know precisely all the syntax and all the, peculiarities of language, because this is going to be, given to you by these models. So I hope that answers the question. Yeah. But yeah, okay. I mean, we can have this discussion. I'm still wondering if you guys want to hear anything about specific hardware examples of accelerators. Yeah.
Cerebra's one, that would be very interesting, because it's such a big chip, and I believe they just have SRAM. They don't even have DRAM, and like what advantages it has, what disadvantages compared to NVIDIA.
Okay. Well, you win the race. Now everyone is going to hate you for hearing about Cerebras, but yes, definitely, we'll do that. And I mean, let me start by saying that Cerebrus, we talked about these data flows, output stationary, weight stationary, Cerebrus uses massive weight stationary. So that's the whole point about only having SRAM and not having DRAM. Because, and again, that's the reason in the Iris thing, when it's a small chip, 24 by 16 or whatever. So when they say weight stationary, it means weight stationary, but then you replace the weights. So you load a set of weights, you do the computation, they replace the set of weights, you do the computation. It's weight stationary for the computation, but you bring weights in and out. For Cerebrus, you just bring the weights once and they stay there forever. So that's why they can get so much performance, because the only thing that comes in and out are the inputs and the outputs. So the weights, and that's why, they can afford to do that because they are wafer, and if they don't fit on one wafer, they put multiple wafers. So it really, that's why they don't have the DRAM. They do not need to bring weights in and out. So that's kind of it's a very brute force idea, but that's what it is. So so let's talk, and I'll try to keep it relatively brief. But you notice this, that in most of my presentation, I'm trying to give you a historical thing, and things that happened before you were born. Sometimes not before I was born. I was born so long ago that but when I was a very very young person. So in wafer scale integration is not a new idea. So again, in the 90s or 80s even, people were trying to do wafer scale, and again, the goals were kind of similar to Cerebrus, basically to, if a chip is good because you can have a lot of stuff, then a wafer is even better because you have even more stuff. And, there was a conference on wafer scale. There were books on wafer scale. There were, articles in magazines about wafer scale. And yeah, so I'm not going to go over this, but this is kind of the introduction to chip and the fabrication. But again, the idea is that with wafer scale, you kind of stop at this stage. You don't dice them, but other than that, you go through the same process. Why is it not? Okay. So again, the big problem with wafer scale is yield. Probably all of you are VLSI people, so you know about yield. Actually, to have high yields, you need to go in the other direction. You need to go to small, to small dies. And the other problems, and these are true for Cerebrus nowadays, the packaging is a really big problem. I should also mention something interesting, that, in the old days, when people were talking about wafer scale, they really meant the whole wafer, a circular wafer. For whatever reason, Cerebrus has decided to make it still a square, which means they lose about a third, I think, if you do the computation, pi r square versus whatever, 4r. So it's basically 3.14 versus whatever, or 2r. And yeah, 2r versus 2r squared versus pi r squared. But and I actually asked, I talked to someone from Cerebrus and asked about this. Part of the reason it was packaging, because having a kind of a round package is kind of difficult. Anyhow, so this is the first Cerebrus. Now they are already at second generation. But again, the more than 1 trillion transistors. And again, if you think in terms of Moore's law, when people say, well, Moore's law is dead, well, it's not really dead because we can now have, 1 trillion transistors in one of these, major chips. And this is the comparison of, the largest GPU at the time. So I think right now it's more than 100 billion. But still, tens of billions versus trillion, and 46,000 millimeters square versus 1,000 millimeters square. So it's pretty massively larger. It's the largest square die, and again, I made already the comment that they are really losing a lot of this area that could have been useful for computation. Again, it looks in many ways very similar to the Iris thing that we saw. So it's still, like I said, there's not that much that you can do on a flat chip. A two-dimensional array is kind of what you do, and there are 400,000 processing elements. They are more complex than the processing elements in Iris. So there is a multiply and add. There is SRAM memory. Again, the weights, all the weights are in this wafer. There is some control and some switch fabric. This is, again, very cartoonish, and I'm not going to get into details. Again, it's the multiply and add is not on vector and matrices. It's on these tensors because, again, you want to process multiple vectors and multiple matrices simultaneously. So it's really 3D tensors. The weights are the ones that are 2D, and I guess it's because they are stored, on these. So here is this weights that are local. So, and again, by distributing the memory this way, they deal kind of implicitly with the memory wall. There is still a separation of memory and processors, but, you can think of it that the processors, you can think of it that, all of this is like a big memory, and then you have the processors inside the memory, if you want to think in terms of the memory wall, so that you have the processor next to the memory that's needed. Something about the 2D mesh. Again, there is something about the data flow, basically. Model parallel versus data parallel. So this is, again, related to what we were talking about in the morning on how you combine together, images together or kernels together in parallel. So that's really what this means, this model parallel versus data parallel. Again, it's a data flow arc, and it's a multiple instruction, multiple data. So again, this is back to Flint's taxonomy that we talked about. So each processor has its own program. So it's not like a GPU where and in that sense, it's a little bit less efficient, but it's more flexible because, they can operate independently. So this is how they distribute kind of a model on on the wafer. And again, because the weights are stationary, you get more area for the layers that are more complex, and smaller area for the layers that are less complex. Yeah.
You have to design your own compiler because it's
Oh yeah. Yes. I mean, we had yesterday, I think, right? We had the discussion about CUDA and GPUs and all that. And I have many other examples of accelerators. For all of them, the compiler is probably 10 times harder and more important in many ways than the hardware. It's unfortunate for us. We are all hardware people, but literally, yes, the software, the compiler is so important. And it's true, like I said, for all of them, because and all of them, and again, because there is this competition, right? So all of these guys compete against each other. They all need to be compatible with the kind of things that you are doing for your assignment. All these PyTorch and all that. They cannot afford to have different ways to represent the model and all that, because so they need to take the kind of code that you are literally. This is exactly the case. So the kind of code that you are using, they need to take it and compile it for this very different, very spatial type of architecture. Yeah, I cannot imagine how hard it is to do that, but yes, absolutely, you're right.
Compiler choose an optimal number of P's and optimal shape for every layer. So this optimal number of P's and optimal shape will vary across the model as well.
Absolutely. Yeah. So it's very complex, very complicated. Yeah, I do not envy the software people. Yeah, so here are examples, and again, in the interest of time, we don't have that much time. How they work. For different types of so again, the important thing is they keep the entire model in the on-chip memory. And again, this is the discussion about the compiler. And yeah, so here are the layers fitting on the wafer. And yeah, so there is also talking about CAD and EDA. There is a place and route kind of aspect to this. There is a floor planning aspect. So yeah, everything is there. I'm not, again, I do want to finish in a few minutes. So here is the discussion also about throughput versus latency. That's the other thing that they are proud of themselves, that because of the way. So for GPUs, you need to have really large batch sizes in order to kind of keep them busy. The advantage with them is that you can have very small batch sizes, and you can get good latency in addition to throughput. So that's kind of one advantage. They have some algorithms to do pipeline versus parallel. And again, I'm not going to go into details. This is kind of a data flow example on the wafer. And here is the kind of the spatial distribution of the computation. So basically you have, the input coming at the top, and then, you have the different layers, and then you have the classification output at the end. So they had to go through hoops with TSMC because, again, the way IC fab works, you have to have dies. You have the stepper with the masks, And, you know, there are these regions in between dies that are, you know, you cannot have, you know, wires or active devices or anything. So they had to work with TSMC to create a post-processing. So they first make the wafer regularly, but then they go and they add wires on top that connect these, you know, the mesh together. So this, I mean, they were very proud that they got TSMC to agree to do that for them. Then yield is obviously still an issue. So because of that, they need redundancy, a reconfiguration. And this is, again, nothing new. Again, if you go back to the 90s when wafer scale kind of was first proposed, I would say at least 50% of the papers at the time were just about, you know, how to do, you know, how to deal with defects, how to have reconfiguration, how to, you know, again, most of the research was actually in this direction. So they obviously had to do that so that they can basically route around defects. The other, and we talked a little bit about this, you know, it's power and thermals. So the different materials expand at different rates. And when you have a small die, it's less of a problem. But when you have a large die, you know, all these stresses add up. So again, they had to go through some hoops about that. So they created this kind of custom connector that can absorb some of these stresses. The packaging, again, was a big one. And from what they told me, that was a major reason they went with the square shape, because when they talked to the mechanical engineers that were going to do the packaging, those kind of got scared about doing a circular package or something like that. So, and again, you know, imagine, so, you know, everything needs to be aligned to, you know, connect together. So having an alignment over, you know, an area of the dinner plate is really difficult. And again, they had to design their own custom things. You know, so I already mentioned kind of the power and the heat. So you basically have current, the power going, you know, into the wafer, and then, you know, you have the cooling on top. So they kind of, and we had some discussion a few days ago about, you know, solutions for cooling. And so they use basically fluid water cooling to remove the heat. And the current, the power distribution, instead of being, you know, usually we have it kind of horizontal on the die, so they made it vertical. And I should say that this is maybe those of you that, you know, have looked at, you know, more advanced VLSI things. So, you know, TSMC, Intel, all these, you know, kind of leading edge, you know, foundries, they are already working on power delivery, not through, you know, metal 10, whatever the way we do it nowadays, but through the back side. So basically have power on the bottom of the die and, you know, through vertical. So kind of the same idea, to have the power instead of distributing laterally, to distribute it vertically, because, you know, that's how it works better. And again, that was until, you know, that was the first generation. This is the second generation. You know, even larger, and it's in 7 nanometer. Yeah, so I guess, similar, but everything, more of them. Something also that, and with this I'm wrapping up, it's a little bit like the discussion about the compiler. For all of these modern, high performance AI accelerators is no longer just about having, one accelerator. Even when that one accelerator is a wafer, it's, it's still not large enough and powerful enough to do meaningful things nowadays in terms of AI. So all these companies, all of them, they need to work, yes, on the accelerator chip, but then also on the software and all that, but also on the system, and by system, I mean, these racks. So you really, all of them have these, basically server racks where they have many of their own accelerators. And you can see here up to 120 trillion parameters, in one of these. And that's how they can basically support, these massive AI models that,
So,
yeah.
Can you go back to the power delivery network? That PCB one.
Yeah.
So the power delivery, we know there are different metal layers on the PCB. So let's assume that it's a 8 or 10 layer PCB. So you are telling me that I have to drill the holes all the way from metal 10 to metal 11, then bring the power to basically silicon, right?
Yeah, but right. But again, you have a premise, and the premise is that this is a normal PCB. This is not a normal PCB. This is in the same way that this wafer scale is a replacement for a normal chip. Then whatever this, it's called a PCB board, but it's a different technology. It's a different beast. You basically have these wires probably going just vertical, and it's not it's not the one that you give it to a PCB house and buy pay I don't know $100 and you get some PCBs back. So yeah, I mean, again, if they made custom packaging and this and that, they have a very custom PCB. So I don't know exactly. But yeah, you are kind of asking the question in the context of a conventional PCB, and this is not a conventional PCB. I mean, yeah, it's, yeah. Yeah, so again, and again, there is a whole hierarchy of and the memory. So they still need memory to load these, so once they load the model, it's there, but they may need to use a different model for another application. So, you still need a place where you load that, or, when you power it on, so they have, a special kind of box just for the memory. And then, again, once you have multiple accelerators, in this case, wafers, then you need to worry about how those are connected together. So you have the mesh on the wafer, but then you have a whole network, and they have this, SwarmX fabric that they call is basically a networking where they connect, multiple of these together so that, the whole model fits here, but then there is a need for them to communicate with each other, so they need to go through this, and you see it's a tree kind of connection. I don't know. Probably not, because no, but even for NVIDIA, NVLink again is a kind of a commercial connection that's for commercial small systems. I'm not sure if they use NVLink, for example, even NVIDIA for their cloud things that look like this. Maybe they do. So I don't know. yeah, and again, there are some, so this is, I mean, this is another thing that they are very proud of. So remember Amdahl's law about, you know, when you have parallel systems, you know, if you get the speed up, and they are, you know, very proud that, you know, you can see that for, depending on how large the model size is, but, you know, for the larger model size, which is 100 terabytes, tera, yeah, tera maybe parameters, the, you know, it's a perfect linear, which means basically, you know, there is no slowdown that you would expect from the Amdahl's law. And the ones that you have some slowdowns is when the model is small enough that doesn't, you know, at some point it doesn't take advantage of the really large. And by the way, here it's, you know, 256 of those racks. So I'm not sure how many, yeah, so maybe, yeah, it doesn't, you probably can do the math, how many processing elements, you know, probably trillions also. Like I said, you know, it's a compiler. So here is the kind of compiler. So, you know, again, on the input is the, you know, PyTorch is one of them, TensorFlow. And then, you know, it goes through a number of steps to get to the actual executable. So with this, we are done. Now go to your assignments.